We have spent an entire semester working on the foundations of calculus. We have constructed the real numbers, we have derived formulas for limits of functions. Now we're ready to do some real calculus, computing some derivatives. So we're going to define the derivative in this video. We're going to compute the derivative of a specific function and then show how to derive more general derivative formulas when we have an unknown function but we assume we know what the function is and what its derivative is. So suppose you have a function that is real valued, and suppose you have a number a that is in the domain. Then the definition of f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. I really like this form of the definition because you can see the slope formula in there. But the version that you probably remember from calculus is the limit as h approaches 0 of f of a plus h minus f of a all over h. These are equivalent, by the way. If you let h equals x minus a, the formulas are identical. And notice that h goes to 0 precisely when x goes to a, so those limit formulas are exactly the same. Alright, so let's go ahead and use those. We'll use both of those formulas to find the derivative of the square root function. So here's our derivative of our formula for the derivative. Limit as x approaches a, f of x minus f of a over x minus a. We plug in our formula for f of x. And now one of the things that is super annoying about finding limits for derivatives is that the denominator as x approaches a always goes to 0. So if we could, but x never actually gets to a, right? That's from the definition of limits. So x minus a is never actually equal to 0. But that means if we can cancel it out, maybe we can make our computations a lot easier. So we're going to do that by multiplying top and bottom by the conjugate. When we multiply that out, we get x minus a on the top. And then on the bottom, if we keep that factored out, we get x minus a times square root of x plus square root of a. And now we have a factor of x minus a on the top and bottom. We can cancel those out. And we end up with the limit as x approaches a of 1 over square root of x plus square root of a. Now, before we go on, I want to make a couple observations. First of all, it turns out it's going to be very important to know that the square root function is continuous, because as x approaches a, what is square root of x getting close to, right? If we don't know it's continuous, we can't just put in the value of a, right? So, but we do know the square root function is continuous. Since its inverse function, the square function, is continuous, and anytime a function is continuous, its inverse is also continuous. So it is. So finding that limit is not going to be a problem. And we also know that we can use our general limit theorems on 1 over square root of x plus square root of a. So what do I mean by that? Well, remember we had those theorems that said if I know the limit of f of x and the limit of g of x, and I add those together, then the limit of that function is just adding the individual limits together. And so we had those formulas for addition, for subtraction, for multiplication, and for division, and we're going to use those on this particular limit. So when we're taking the limit as x approaches a of 1 over square root of x plus square root of a, that is the same as the limit of as x approaches a of 1 on the top, and on the bottom, the limit as x approaches a of square root of x plus the limit as x approaches a of square root of a. Now, two of those limits are just limits of constant functions, so those are not going to be terribly exciting, but they're going to be easy. And notice that we have that the square root of x is continuous, so the limit as x approaches a of square root of x is going to be square root of a. So, boom, we get 1 over square root of a plus square root of a. If we simplify the denominator, we get 1 over 2 square root of a. Now, you may prefer the h version of the derivative formula, so let's go ahead and do that one too. It's pretty much going to work the same as the other one, right? We plug in our formula for f. We multiply top and bottom by the conjugate. The square roots disappear on the top, and notice we have a plus h minus a. Those a's are going to cancel. When they cancel, we can now cancel the h's, because even though h is approaching 0, never actually gets there, so we can cancel it out. We get 1 over the square root of a plus h plus a. That square root of a plus h is a continuous function, just like the square root function was before. So we can replace that h with 0. We end up with 1 over square root of a plus square root of a, which is just like it was before, 1 over 2 square root of a. All right, so now we're going to use the derivative definition to find a more general derivative formula. And this is going to be super helpful for when we're doing more complicated ones like the chain rule and things like that. That will help us get away from having to use the definition of the derivative every time we want to take a derivative. But we're going to use it on a slightly less complicated one. So suppose we have a function that I'm not going to tell you what the function is, but we're going to pretend like we know how the function works and we know what the function derivative is. And the question is, if you know both of those things about the function f, can you find the derivative of f of x squared? And it turns out we can. Again, by using the definition of the derivative. So we plug in g of x equals f of x squared, g of a equals f of a squared, we get this. And our goal now is to try to involve something that looks like the derivative of f. Now the derivative of f is limit as x approaches a of f of x minus f of a over x minus a. So if we could somehow get f of x minus f of a over x minus a into this expression, we can use the definition of the derivative to help us out. How will we do that? Well, notice that the numerator is a difference of squares. So if we want, we can factor it. And notice there's my f of x minus f of a. That's my numerator of my derivative definition. And on the bottom, we have x minus a, which is the other part of my derivative definition. So if we separate out that f of x minus a over x minus a from the f of x plus f of a, like so, then we have two things multiplied together. We can multiply those limits together. So the left term, or the left factor, I should say, goes to f of a plus f of a. The right factor goes to f prime of a. That gives you 2 times f of a, f prime of a. Pretty nice. So if we know f of a and we know the derivative, f prime of a, we can find the derivative of g. Now, there was a little bit of chicanery that I was doing there. I put that the limit as x approaches a of f of x equals f of a, but I don't remember ever assuming that f was continuous, which is basically what we're saying when we do that limit. And so you might think that maybe I was being a little bit dishonest, but no, actually we're okay. I was okay on that one. Can we do that? You bet we can. As it turns out, every differentiable function is continuous. And you may not remember this, but back when we were doing continuous functions, one of the things I asked you to do is I asked you if we know the limit as x goes to a of f of x minus f of a over x minus a, if that limit exists, prove that f is continuous. You did that, okay? But what I was actually asking you to prove is if f is differentiable, if it has a derivative, then it's continuous. And so I appreciate you doing that because now we can use that fact here, and we did. So yeah, we can do that. All right, so now after all that work, I think you're ready to do the activities for the derivatives. Just go ahead and click at the link below this video, and you can get to work on those.